Everybody, it's Mrs. Dinkelman, and this is the section in Unit 11 about creating a power series. So this is just one of the two techniques that we'll talk about how to do that. Last section we talked about the interval of convergence. So normally what would potentially happen as a mathematician is they would find a power series, they would find a polynomial that matched to a function that they were looking at, and then they would have to test where or when those two matched up well. So I have a little bit of a picture here from Desmos. And really on this one, I had to only use a certain amount of terms because, I just don't have that ability. So let's just go ahead and look at Desmos and you can see this kind of happen. So we're talking about the function y equals 1 over 1 minus x. Oops, that's not a 1 though. Okay, so that's that one. And what I was saying earlier, so look back at here, and that is that this series should match up to 1 over 1 minus x. And we'll talk about why that is here in just a second. But that means I'm going to have an x to the 0, and then an x to the 1, and then an x to the 2, and so on. So let's go ahead and see what that looks like. So x to the 0, and then x to the 1. And here's something I think it's really important to notice. What I've done is I've created the y-coordinate to be the same, and now the slope is the same. So this is really just the tangent line for this function. So now if I add an x squared, now what that technically is like a tangent parabola. So we have the same y-coordinate, same slope, and now it matches the concavity. And what we want to continue to do is to kind of really sidle that up and make it so it's perfect. So let me just do a few more terms here so you can kind of see, because I don't know, I find this super interesting to kind of watch happen, this visual. Okay, and so the question is, I guess, okay, I see it kind of getting more and more perfect, but clearly it's not going to be perfect everywhere because I can't get a polynomial that has this asymptote right here at +1. So clearly that's not going to happen. But is it going to be that this particular polynomial matches this entire side of the graph, or is it just going to match in like a certain area? It almost looks like maybe -1 to +1, not including those. It may be, we'll get there. So that's what we were really answering last section, is where is this polynomial going to be perfect? If I can get an infinite amount of terms, where can I get it to match? Okay, so that's what we were really doing algebraically last section. So now this time we're moving on to, well, if I have a different function, how do I know that this is the polynomial? How do I get it to be that way? And so that's what this power series is about. So like I said, we're just going to do this one technique this section, and then we'll show you another technique. So this is really just based on that sum of the geometric series. So just a quick reminder that the sum of the geometric series is a over 1 minus r, and then our geometric series was really a times r to the n. Okay, so that's all that's really happened here. So in this case, the a is a 1. So you can see in front here we have a 1. And then instead of an r, we have an x. So we have an x to the n. So really that's just how this gets built, is using that geometric series. The other thing that we kind of sort of talked about a little bit last section is where it's centered or where it's perfect. So let's go back to this visual again. Remember me saying I made sure that this y-coordinate was perfect at x is 0, and that was the tangent line when x was 0, and so on. So we have to pick a spot where we want it to be perfect, and that's called the center. And there might be different reasons for us to move the center. Like maybe I really want to figure out what the answer to this is at 4. Well, then I would probably, maybe 4.1 would be a better thing to say. It would probably be helpful for me to make sure that this polynomial is perfect at 4 then, if I wanted to try to plug in a 4.1 to that. And that becomes really important when we get to things like sine or cosine and some of those others, because we might want to know what sine of 3 is. Well, 3 is really close to 3.14159. It's close to pi. So if we make the thing perfect at pi, then maybe we can figure out what's going on or approximate what's happening at 3. So that's kind of the idea behind this center. Where are we going to make it perfect? What do we need? Okay, so there's that. Okay, so using our geometric series idea and always trying to kind of put it into this a over 1 minus r form. That will help us to manipulate all of these things. And we're going to start with the ones that are centered at 0 because that's kind of the easiest thing to do at first. And then I would recommend doing all the ones centered at 0, and then we'll do the ones centered at some other location afterwards. So in this case, if we just think of our a value as 1 again, and our r value is x squared, then we're just going to build that polynomial as a times r to the n. So really we could have simplified or written this a little bit more concisely by just saying x to the 2n. Now one thing I would like to do, and I wish I had done this as the example, but I'm going to go ahead and change it. What if that were a plus sign? Okay, let's just really quickly change that to a plus sign and try the same problem. So let's say that's a plus sign. Well, what I really have to do is manipulate it to be that a over 1 minus r. Okay, so that's what it would look like if I changed that to a minus sign. So now for my a times r to the n, it would look like this. Now more concisely, we might want to write it, you know, it sort of depends. We might want to say, oh, it's alternating and then it's x to the 2n. And there's lots of different ways to kind of write that. But that's what you want to do on those centered at 0 on this first part of the assignment. So just pick out the ones that are centered at 0, try to manipulate them into the a over 1 minus r, and then write that series. And a lot of times they will ask us to write like the first few terms. So just be aware that sometimes we'll have to do that. So if you want to hit pause now and try basically that 1 through 5 and then come back to for the rest, please feel free to do that. Okay, so example 2, we're centered at 1. So what that really means is I'm going to need to have like an x minus 1 in that denominator because I want to make sure that when I plug a 1 in, that term kind of heads towards 0. So I really have to manipulate what's going on the bottom here. So let's see, I'm just going to go ahead and pretend I'm going to use that. So I have to figure out what goes there because I can't just create a new problem. I have to make sure that the denominator of whatever I'm going to create is equal or equivalent to what's in the denominator of my original, which is 4 minus x. So let's just kind of think about what happens. If I distribute that negative, technically what happens is I get a negative x plus a 1. So that means in this position where my question mark is, I believe I need a 3. So that when I simplify, I get back to that 4 minus x. So this is what's going to be in the denominator. I'm going to rewrite it as 3 minus x minus 1. Now, on here, and maybe I should have made sure that we saw this earlier, this needs to be a 1. So I'm going to have to factor a 3 out of all of these, and there's a couple ways to do it. You can just basically divide everything in here by 3, so you could call this 1/3. This could then be a 1. And then this gets divided by 3 as well. You could also just pull a 1/3 out and have it kind of completely off to the side. Make sure you multiply by it eventually, but I kind of like it this way. I think that'll work. So I'm going to say my a is 1/3 and my r is x minus 1 over 3 to the n. So you can tell that this is centered at 1 because of the x minus 1s. So if we were to go back, for instance, to the example or any, I guess, of the problems in the previous section, we can kind of see where they're centered. So this one is centered at 1. This one is centered at -2, because again, think about plugging in that 0 of the function. This one's centered at 3. This one's centered at 5. So you can see what's going on with the center. You can see where they're trying to make the graph perfect by what's going on in there with the x. Okay, so when we center at x minus 1, we'll see that x minus 1 in our polynomial. And just kind of a by the way, just in case they were to simplify this, one other way to write this, and you don't need to do it, I just want to make sure you would know to recognize it, is this could be x minus 1 to the n, and this could be 3 to the n plus 1, because basically there's an extra 3 down there for that one. Okay, so get going on finishing the rest of creating those polynomials, those power series.